Welcome everybody to our conference. Today, Dr. Kodari and I will be talking about the exoplanet K2-19c.
Welcome to the first part of this video. In the first part of this video, we're going to explain briefly the three different parameters that have been done in this project. In the second part of this video, we're going to get into more details and explain the different parameters of the calculations, of the inferences, and in the light curve graph. However, in this first video, we're only going to briefly explain the whole three parameters. So let's get started. So the first parameter is all the descriptions that have been done to find our exoplanet. So once we have done our research, the first parameter sheet is all the descriptions for our planet. So like the planet ID, total duration, full duration, planetary mass, planetary radius, and etc. So all the descriptions that are linked to our exoplanet. In the parameter sheet 2, it is the inferences. The inferences are based on three topics: possible composition of planet, season, and atmospheric composition. So those three different topics will explain if our planet is viable or not. However, we'll get into more details in the part 3 of this video. And lastly, image of a normalized light curve. So once we have the data, the whole data of the brightness in relation to the Julian days, we normalize all those data points and we insert it into a graph maker, and it created a beautiful light curve. But we'll get into more details in the second part of this video. Welcome to the second part of this video. So in the second part of this video, the whole task is to briefly present what the calculated parameters are. Let's get started. So the first calculation we did for one of the parameters is the total duration. So the total duration is the time from the beginning of the decrease in brightness to the end of the rise. So once we have our light curve, it has a dip. So the total duration is from when it decreases to when it increases, the whole duration. After that, we have the full duration. The full duration is right under the light curve, and it's the amount of time the time of the planet is fully over the surface of a star. So we have our light curve, the total duration, and the full duration is just the bottom of the light curve, and that's the time where the planet is completely over the star. After that, we have the planetary mass, which is self-explanatory, planetary radius, volume. Now we have orbital period. The orbital period is the time that it takes for our exoplanet to do a full lapse or a full circle over the star. So for Earth, it's 365 days, obviously, but for our planet, it's 0.0217 Earth years. After that, we have semi-major axis. First, we have what's a major axis? The major axis is the ellipse that one celestial body has over another. So it's basically the distance between two planets. So, and a semi-major axis is half of that distance. However, a major axis is a full diameter. So it can be, semi-major axis can be like the radius. So it's not like the radius, it is the radius. Sorry. Now we have eccentricity. The eccentricity can be described with two values. So it can be with 0 or 1. So if you have the value of 0, it means that our planet resembles more to an orbital, circular orbital. If it resembles more to the value of 1, it resembles to an elliptic orbit. So and afterwards, if we go over 1, it looks like a hyperbola. Then we have the inclination and stellar luminosity. Stellar luminosity is the brightness of our star. Next, we have axial tilt and atomic spectra for our atmosphere. However, those two parameters were not calculated.
In this part of the video, I will be talking about the last parameters. So the possible composition of the planet, the season, and the atmospheric composition. So what type of molecule are in the atmosphere. So let's start by the possible composition of the planet. We compared it to a planet that we already know, Saturn. Saturn is mostly based out of hydrogen and helium. The center of Saturn is mostly nickel and iron, but there's also other metals. We compared it to Saturn because it had similar density. Now for the season. We all know that on Earth there's 4 different seasons: summer, fall, winter, and spring. What causes these seasons? It's the tilt of the planet. So when the planet is on one side of the sun, the northern hemisphere will receive most of the direct rays, so it will be summer in the northern hemisphere and winter in the southern hemisphere. And when it does 180 degree turn, so half a loop around the sun, it's now the southern hemisphere who will have most of the direct rays, and therefore summer in the southern hemisphere and winter in the northern hemisphere. For a planet, we weren't able to found the axial tilt, so we will assume that there's no possible season. Also, the period of our planet is only 7.93 days, so that's not much for season or big change in seasons like we see on our planet. Now for the atmospheric composition. We also compared it to another planet we already know. This planet is known as Venus. So we compared it because the temperature on Venus and the temperature on our planet is pretty similar. It's around 745 Kelvin for our planet, and for the Venus it's 730 Kelvin. Okay, would this planet be viable? Definitely not. If you only look just at the temperature, our body couldn't handle any temperature above, let's say, 100 degrees Celsius. And on this planet, it's above 400 degrees Celsius. And there's no really oxygen or water, two main nutrients that your body needs to survive.